Hello, everyone. Welcome to Discover Anemoi, our series of training webinars. Let's give it one more minute. We have a lot of people still joining. So today's webinar is the second webinar in our series. And today we'll be covering Anemoi graphs and Anemoi models. Then there is one more webinar planned in this series. So the next one and the last one is on Anemoi training, Anemoi inference. So that's taking place tomorrow, also at 3 p.m. Central European summertime. All webinars will be made available to rewatch, so if you missed something, you'll be able to catch up. Now, today's webinar, we'll be covering Anemoi graphs and Anemoi models. So you'll be seeing two presentations, both by my colleague Mario. We have earmarked a Q&A session, two actually, one after each of the presentations. So after the first presentation on Anemoi graphs is over, we'll be dedicating a few minutes to just answering the most pressing questions, because we do want everything to be very clear before we move on to the next presentation. And then afterwards, just like yesterday, we're going to be taking quite a few questions at the end. Don't necessarily wait with your questions until the Q&A. Please do put them in the chat, especially if it's something pressing that you would like clarified. And then we have colleagues who will answer that in the chat for you. And then after the second presentation, we'll have a more extended live Q&A format. A couple of notes. So this webinar will be or is being recorded, and we'll make the recordings available on the webpage very soon, along with the PowerPoint presentations. We would also like you to ask you to refrain from adding any AI meeting assistants or note-taking bots of that sort. So please disable them now, and we will also be going and removing them as they join. I see there's an echo. Is the sound all right? If someone else can confirm.
I don't hear any echo.
Okay. So if you have any questions, you can always contact us at training@esnwf.int. And I think now it's time to move on to the presentations. So I will introduce Mario to those who don't know him yet. He's held quite a few presentations and trainings here. He's a machine learning scientist at ESNWF, where he works on the development of AI-driven weather and Earth system forecasting models within the Anemoi framework. And his research interests include the integration of observations into operational data-driven forecasting systems, as well as multi-domain modeling and training strategies with multiple data sets and high-resolution modeling. And with that, Mario, over to you.
Thank you, Julia, for the introduction. So, welcome everybody to this webinar series. First of all, we will start today with a presentation about Anemoi graphs. I know that you have been already introduced yesterday through Anemoi, but just coming back to this, Anemoi is an open source ecosystem to train weather and climate models. It is developed by the ECMWF and the member states, and it goes end-to-end, meaning that it goes from the creation of the dataset to the training on the models and then serving those models for in inference. And it has a wide range of users, right? From individual researchers and contributors to research institutions and also operational med services. And all of this ecosystem, we say that it is ecosystem because it is a group of Python packages, right? It is not only one package, but a group of Python packages that work together. And yesterday, after the introduction, you already had the overview of Anemoi dataset, that it is the package focused on the dataset, but then there is a few others that relate that play together to get the full capabilities of the ecosystem. And today we will move to the other two core components of training a model. So for training a data-driven model or any model here in Anemoi, we need three basic things. One is the data set, another one is the graph, and the third one is the model. We are covering now in this series the second one, but just also trying to refresh what you were told yesterday by my colleague Harrison. The dataset is just a ML-ready copy to make the training of these models very fast. So it's just optimized for the I/O operations to be really fast. So it is just a copy of the data. This is one of the most important things to know about the datasets. And then these copies are in are SAR datasets that are easy to chunk. And the main component that we'll handle in this in this webinar is the graph, right? And why is important the graph? Because the graph will define how the data flows. So the nodes and the edges of the graph will define how the data flows from the input to the output, what in weather state is from the previous weather state to the next weather state. But in other use cases like downscaling, it can be how the information from a low-res image to a high-res image flows, right? So if we have edges that are very long, then we will provide the model the opportunity to learn some longer connections or longer relationship between the nodes. If we set the edges to be very short, then we restrict the model to learn only very local relations. So the graph here plays a key role on how the model performs later. And the third part that we will be covering this in the second presentation of this series is the model, that is just a PyTorch model. And here in Anemoi, one of the main things to know is that Anemoi only support graph neural networks, right? We don't have to worry about this because we will go through it explaining from the beginning what's a graph neural network, and it is also the most general configuration that we can have. So coming back to the graphs and Anemoi graphs, Anemoi graph is the tooling, the Python package that we have to create, design, customize your graph, and also inspect those graphs. This is a Python package that is based on YAML recipes. So the way that we interact with it is normally through a YAML. And then in this, we have two different things. The two main blocks of the graph are the nodes and the edges, right? So the nodes will normally represent locations in the earth, and then the edges, how these nodes connect. And then we have a third block in Anemoi graph that it is the attributes. So this is extra information that we give. It can be node attributes, so information that we would give to the nodes, or it can be edge attributes, information that we get to the edges. So one example here would be the edge length, right? So we connect to nodes, and that's already an edge, and then we can add on top of that extra attributes like the edge length or the direction. For example, those are two of the most common attributes used in weather systems. And we say that the interface with the user was a recipe YAML, and then we use that recipe most of the time through the command line interface. So we have a few commands like Anemoi graphs create to create a graph based on a recipe, and this creates a heterodata object that it is a PyTorch geometric object. So this is not something specific to Anemoi, but it is something used also outside of the Anemoi community. It's something that we are inheriting from the open source ecosystem. And then we can use some other commands like describe or inspect to analyze that graph already created, right? So here, instead of specifying the recipe, what we do is go to specify the file, the .pt file. This is the heterodata object, and the describe will produce this log that we see here with some meaningful statistics about how many nodes we have or what are the edges that we have defined in that graph. And later also with a spec is similar to describe, but here you also generate some visualization plots. These are interactive plots, so you see that there are HTML files that you can inspect and play with them. Now we know what's more or less a graph, right? We know that it is a set of nodes and edges, but here what we are interested is in using this to define how the data flows. So there is a close mapping between the graph and the model, and here the models they follow the models in Anemoi mainly follow this encoder processor decoder architecture. It is also sometimes referred as a unit, or that it has this characteristic shape like a bottleneck, where the information is encoded. So it is also important to have this in mind to know the relationship between the graph and the model. So here the first thing to know is that the nodes, there are two main types of nodes. One are referred normally as data nodes, and they represent locations of the input or output data points. So this is where our physical variables are defined, where our data set is defined. And then the other set of nodes is the hidden nodes. These nodes normally are at a coarser resolution compared to the data nodes, and they are used to compress the information, right? So in the weather forecasting use case, we will have only one set of data nodes, right? That because the input state and the output state is the same exact node. So what we do through a model prediction is just update the values of those nodes. But there are other use cases like downscaling, for example, that we have two different sets of data nodes, the low-res data nodes and the high-res data nodes, that they are not the same. And the low-res will be our input data nodes, and the high-res will be our output data nodes. So these two set of data nodes, they don't have to match. So now we can see, we said before that Anemoi graphs needed a recipe file to create the graph, and we see here one example of this recipe file. We see that we have here the same two blocks mentioned before. We have the nodes and we have the edges, and the first thing is define the nodes, right? So the first key that we see below the nodes, that we see data and hidden, that's the name of that set of nodes, right? So what we are doing with this recipe is defining two set of nodes named data and hidden. And for those we use two different node builders, right? So here this package is quite flexible. You could implement your own node builders and reference them in the recipe without needing to install anything else, right? So you are specifying directly a class that can be an Anemoi Graphs Edge class, or you can implement your own node and edge builders. Then we move to the edges and we have a similar structure. Here we have to define for each specific edge builder what's the source and target set of nodes. So in the first case, we see data hidden. This is the encoder edges, so the edges going from the data to hidden. And for this, we use a specific edge builder. And then for the other two, we will use two different edge builders. So this can be very configurable, so you can play with different options for each of the edges, set of edges. So coming back to the node builders, that first of all, the data node builders, as they are data nodes, they match with the physical locations of our data set, right? So normally for all of our data nodes, it's quite straightforward to use this node builder that is the Anemoi dataset nodes, and this will create the data nodes copying the coordinates from the dataset, right? Which makes completely sense because that's what you are trying to represent. And then the thing is using other node builders for defining the hidden grid, right? Remember this hidden grid, this is the cursor resolution that we will try to use to compress the information in the unit. So for those who have experience, maybe not with graph, but with convolutional neural networks, where we have this unit, this hidden would represent the bottleneck in the middle of in the unit, the cursor resolution. And here, for example, what we are using is another node builder that it is named trinodes. The name comes for triangular refinements. The idea here is that we cover the sphere with an icosahedron, that's 20 faces, and then with the resolution, we specify the number of refinements that we want to apply. Each refinement will split a triangle, each of these faces, into 4 smaller triangles, right? And then each triangle matches with one node. So refinement level 6 will have 4 times more nodes than refinement level 5. So we have now covered the two most common node builders, and now we go to the edge builders. As mentioned before, for the edge builders, we also have to specify the source and target nodes name. So in this case, you see data and hidden, and then we go through the edge builder, that it is the same as for the nodes. We can specify here any class. In this case, we are using an Anemoi graphs class, but you could implement your own custom class that you can use in the recipe. Here, for example, just to give some explanation of this method, this is the cutoff edges, and this is as easy as connecting for each of the target nodes. So in this case, it's data to hidden. Hidden is our cursor set of nodes. For each of these hidden nodes, what we do is we draw a circle around that target node. You can see here the red circle, and we connect all of the source node or blue nodes within that circle to that target node, right? So the nice property of this method is that we can maximize the information that flows from the data to the hidden, right? The encoder what we are trying to use is as much information as possible from the input data. Then the second part of the second set of edges we define from data to hidden, and the second part that we define is from hidden to hidden, what we will reference later with the processor. In this case, we could use a distance-based method like the cutoff, where we draw a circle, and this is a distance-based method. But we can also rely on the topology used for creation this mesh. If you remember before, I was talking that we had iterative refinements where we were splitting each triangle in smaller triangles. So here we have the notion of a neighbor, and we can rely on that notion just to define what are the connections. So with X hops, we mean that we connect each node to the neighboring triangle, right? Easy. The nice thing about this multi-scale is that multi-scales refers to doing this connection at every refinement. So what we get is that, as you see here, this node has at refinement 6, it has 3 neighbors, but at refinement 5, it also has another 3 neighbors. So we create this combination of shorter and longer connections in the graph. Then later, the last step or the last set of edges would be the decoder, the edges going from hidden to data. Here we are using different graph configurations, but you can also use the same for all of them if you want. So this is very configurable. It's just to show, to present some of the different possibilities that you have. In the decoder, we use just a normal edges, that just means connect to the nearest neighbors. So in this case, we use 3. This means that for each target node, each data node, we will connect the 3 nearest neighbor. And with this, we are able to get information from the whole boundary of the target node. So in this case, we presented an example of a graph recipe to define an encoder processor decoder, because we define 2 set of nodes, the data and the hidden, and then 3 set of edges, encoding, processing, and decoding edges. But we can Anemoi graphs enables a more complex use case. So this could go to something like a hierarchical model, where we don't only have one hidden set of nodes, but we have 2 hidden set of nodes. And we there it is as easy as defining your first set of hidden nodes and your second set of hidden nodes, and then the corresponding edges between them, and then you get a graph that you can use later in Anemoi training. And the same also, so we covered here the example with one data set for weather forecasting, where we were taking the same dataset input as an input and the same dataset as an output. But if you want to do something like downscaling, or you want to just have 2 different Earth system components, 2 different set of variables, where the grid is different and you cannot concatenate through the grid dimension, you can still use Anemoi, and you can still use those 2 datasets. You will have to define 2 different set of nodes, and then you can define your different encoding edges to the same hidden, and then that hidden representation will fuse those encoded latents. But the idea is that Anemoi graph supports this functionality, and also Anemoi training later. Another thing that I've been talking all the time is about global graphs. But most of our users in Anemoi are interested about local models, right? Regional modeling. So Anemoi supports not only global graphs, but also 2 different types of regional modeling that are referred as limited area graphs and a stretch graph. Here, the main difference is that we will use 2 datasets, one dataset for the area of interest, the region of interest, and another global dataset as a boundary, as a conditioning of the boundary, right? And the difference here is that the limited area graphs will have just a small boundary through the region that is considered only as an input. This is the key part, only as an input. Then, so this in our operational setup later, you will have to feed this boundary with a global model prediction. And in the other case, we have the stretch graph that it just has a global coverage. So the stretch graph has a global coverage as a global model, but it just has 2 different resolutions, right? So in the region of interest, it will have a higher resolution. It can go up to your dataset, like 1 kilometer, 3 kilometer, whatever you have. And then in your global domain, it may have 25 kilometers or 5, right? But in this case, the global is passed as an input, but also as an output of the model. So this model will be always self-contained in inference, so you don't have to feeding new information for rolling out that model into the future. So let's go how this looks in the recipe, right? The first thing to do is using some of the Anemoi datasets operation that were presented yesterday, in particularly the cathode operation, to put together 2 datasets. So that's what we use, the cutout operation, to specify our local Anemoi dataset and our global SAR dataset. And this will combine those 2 datasets. And the other key part here is that we have the option to define attributes. We cannot forget about this. So what we will use is define a cutout mask attribute that just it is a Boolean mask for the data node. So as you see here, this attribute is under the data nodes, right? So this will be an attribute of the data nodes and only the data nodes. And this is the cutout mask, right? Cutout. So this is an attribute that it is only possible to create when you are using the cutout operation. If you are not using the cutout operation, you will get an error. And this cutout mask is just the Boolean mask for the data nodes, showing which nodes are in the region of interest and which nodes are outside of the region of interest from that combination of nodes. And then we go to the hidden nodes, and that's where we will have to specify some extra information. So I don't know if you remember before, but the node builder that we presented was called try node. So now we have two different node builders for each data set, each use case, the limited area and the stretch graph. One is the limited area try nodes, and the other one is the stretch try nodes. In the first one, we only specify one resolution because this is the resolution of the region of interest. And then we have to specify the reference node's name. So this is the name of our data nodes. Here is data. And then also the attribute name that we want to use for defining the region mask, right? So in this case, we call it this cutout mask. This has to match with the name that we put it to that attribute. Similar for the stretch grid, we have these two same arguments to define what's a region of interest, right? So remember, these two last arguments are used to define what's the region of interest, right? What's your regional model, right? So our regional model is the data nodes, but not the whole data nodes. It's only the cutout mask of the data nodes. And then here in the stretch try nodes, what we can see is that we have two different resolutions, right? As we said before, the stretch graph has a high resolution, or you can also set lower resolution, but the idea is that you set a high resolution in your region of interest that you are most interested in, and then you have a coarser resolution outside. So with this, we can see the full example there with the edges defined here. And here, one important thing is to look also. We show an example of how to define node attributes with this cutout mask, and we see here also an example of how to define edge attributes, right? So this is with an optional attributes key there under the edge configurations, and then we specify any of the different attributes offered by Anemoi graphs or your own attributes. So just as a wrap up, before going to the questions, Anemoi graphs is used under the hood by Anemoi training. So normally you don't have to call Anemoi graphs, you still can, and you will be able to load those graphs from a file in Anemoi training. But the normal use case is just having your graph recipe in Anemoi training, and training is able to create the graph on the fly. But it is extremely useful to inspect and debug those graphs that you are using in training to know that they have the connections as you expect. And I think those are the most important things. So also the configurability option. So you have the support of using Anemoi graphs classes, but you can also implement your own ones and refer to those through their same recipe files. So in that sense, it's thought to be used by any user and develop on top of what is currently there. So with this, I am done for the presentation. Feel free to I don't know what's is it raise the hand and ask the question, or
Yes, we can. Yeah, thank you, Mario. We can first go through the ones in the chat because there have been quite a few actually, and Anna has been answering some of them, but a few we would like to raise. So I'm going to read them out, and then if we have time afterwards, people can unmute themselves as well.
Perfect.
So Rashad is saying he has two questions. Anemoi's encoder-decoder GNN maps data through a hidden mesh and back. Since the encoder and decoder are separate graph connections, could we use a coarse resolution grid as input and a fine resolution grid as output to perform spatial downscaling? And if so, what modifications would be needed to the data pipeline and loss function to support different input and output grids?
Yeah, good question. So I think this is already supported. The idea is that Anemoi supports multiple datasets, right? So what you can do is just define multiple datasets, being this in this example being two datasets, low res and high res. And one of those datasets, the low res, you are not interested in the output. You are only producing you are only using it as an input. You are only providing forcings variables. And then in the other dataset, you are you only care about uh, the output. So that's like a diagnostic. All of those are diagnostic variables. So the input and output for each dataset is always the same, but in reality, you are not using the output for the low-res dataset, and you are not using the input for the high-res dataset. I don't know if that's clear.
Yeah, thank you. There's a follow-up question there. Is it possible to downscale with some technique without target data, with only input?
I mean, you will need, I don't know what's exactly what you mean with target data. You will need the target data to train the model, to do like to compute the loss and then back propagate and update the model parameters. You can do some kind of interpolation that's supported in some parts of the code, but you will still need target data to compute the loss. I don't know if you mean like having that target data. The other thing, in some cases, what we don't have is information, physical variables for some nodes, right? That's the example of the hidden nodes. You don't need physical variables for all set of nodes, right? You can use only the coordinates. So when we encode information from data to hidden, the only thing that we know about the hidden is the coordinates, so the latitudes and the longitudes. We don't have any physical variables there. I don't know if what of those two options you were referring to.
Okay, thank you. Next one. What technical factors drive Anemoi's heavy focus on GNNs over other architectures like vision transformers or FNOs? Does it stem from a performance advantage of GNNs in modeling multiscale atmospheric dynamics over other strategies?
I think it's a mix of all of them, right? So the graph is the most generic one in the sense that you could handle like any vision model like a CNN or a vision transformer can be defined as a graph neural network when you have like each pixel is one node and you just connect with the neighboring pixels. So it's the more generic one. It also makes a lot of sense for earth science, where we are planning to integrate observations that they are sparse and that they and then like the performance wise also, it is very easy to chart and scale the graphs. So for us, it's been like multiple reasons what made us take the decision to focus on graphs.
Okay, thank you. Let's do one more and then we probably need to move on, but our colleague Anna is going to be typing away in the chat to answer more of your questions. So the last one is, can you explain a realistic approach for a regional model? What would be the target data set to train on? Error 5 data. How can one train a high-resolution regional model? Don't you need high-resolution observations in a grid form that the model will learn upon?
Yeah, so the normal use case for regional modeling is using ERA 5 and then a regional reanalysis. And then you will do the cutout of those two datasets that we saw before in the example. And you can use either the limited area approach or the stretch grid approach, but the idea is that you will combine your regional reanalysis with a global reanalysis like ERA5. Because then later if you are planning to serve that modeling operations, then you will need like the initial conditions for those datasets. So the global conditions, you can get those from the operational analysis offered by ECNWF, but then you will also need the initial conditions for the regional domain. So, but you will need some regional reanalysis, high resolution regional reanalysis.
Okay. Thank you so much, Mario. I think we can move on now to the next presentation.
Okay.
And then we'll have more Q&A time at the end. But please keep on putting your questions and we'll be answering them in the chat.
Perfect. Thank you, Julia. Okay, so now let's go with Anemoi models in this second part of the webinar series. Now, for those who will be following offline, just go back to Anemoi. Anemoi is this open source ecosystem when we have multiple tools to go to train data-driven weather model, and this goes end to end, right? This goes from the dataset creation to the inference going through the training. So Harrison covered Anemoi datasets. I cover Anemoi graphs in the last session, and now we'll focus on Anemoi models. That is the third component that we need to train a model, right? Then later, in later sessions, we go through Anemoi training and inference. So here we have a schema of the main components of the model, a diagram of these components. We have the interface. This is the Anemoi model interface. This is the envelope of the models in Anemoi, and it has different components that we will try to go through it today. So first of all, we start with the base, the core component, that it is the model itself, what we talk about, what we refer as the encoder, processor, decoder. And in this case, coming back to some of the questions that I saw in previous lectures, Anemoi supports only graph neural networks. This is a decision that we made on purpose because we think that the graph neural networks are a good fit for earth science, in the sense that you have that flexibility to define the connections in the data. It works well with unstructured data, so you don't have to establish constraints on the grid. It extends nicely with observations, with sparse observations from satellite data or from stations. And then also it is easy to, not easy, but it allows some efficient scaling by distributing over different GPUs. And the idea here of a graph neural network, the main difference with a dense neural network, a convolutional neural network, is that these neural networks operate on graph data, right? So they take as an input a graph, and the output is a graph. That's the main difference. And within this category, there are different types of graph neural networks, right? So one example is node classification, where you take a graph and then you output a graph. And what you are interested in this output graph is a label for each node. This is called node classification. It could be also graph classification, when instead of having a label per node, you have a global label, but this is again a graph neural network. And then you have link predictions, when you create or delete some edges. This model is used very frequently in social for recommending systems. And then the third one would be the node regression, right? That is our case. So in the graph neural networks of Anemoi, we don't modify the structure of the graph. What we modify is the node features. So these represent weather states, right? So we try to update those weather states, how they they progress over time, for example, for a weather forecasting task. In this case, it's important to know what information is used to update these node futures. For updating the node futures, consider myself as a node. What we will do is I will ask my neighbors, so I will look at my connections to other nodes, and I will use the information on those other nodes uh, plus the information in the edges, right? So you remember that we have node attributes and edge attributes, so all of this information. So for each of these neighbors, we will create a message, right? So I will look for all of my neighbors and I will create a message for each of those where the source node futures are taken into account and also the edge futures are taken into account. Now that I have multiple messages, I will aggregate those messages together. And this is commonly referred as message passing, right? So we keep updating the node futures based on my neighbor futures. This is basically what a graph neural network is. For the case of, so now let's go back to the encoder processor decoder, to the base use case of an Anemoi model. This is the most common architecture that we will see in Anemoi, and also like in most of the data-driven weather models, that's an encoder processor decoder. So first of all, what we have here is an encoder. It is also a graph neural network, right? It takes a graph and produces a graph. In this case, the encoder, it only takes the data nodes, the hidden nodes, and the edges connecting the data nodes to the hidden nodes. So these arrows represent the edges that are also defined in the recipe. It was the first thing that we defined under the edges in the recipe, right? So it takes these three things. We normally refer in the code as a subgraph, in the sense that it is two set of nodes and the edges coming from one to the other. And the output of this encoder will update the node futures of the hidden, right? So you see here some numbers that are the number of nodes and the node future. So we see here a 4 because the only thing that we know about these hidden nodes is the latitudes and the longitudes. And here we use the cosine and sine. So that's the reason that there are 4 values, right? And once we have updated this, we update this to our latent dimension, that in this case is 1000, but it could be something else. But as you see here, the number of nodes keeps the same because it's exactly the same nodes. So then the next step is just processing that hidden representation, right? And this is again just updating the node futures of those hidden nodes. But again, in this case, the number of nodes still it will be the same, and also the number of dimensions. And what comes now? Now it comes the decoding. And here it's important that we use our data node, so to define another subgraph, as we were doing before here. So this will use the updated hidden nodes that are now 1000 channels, and these edges are the edges coming from the recipe file. The edges that we define when defining the decoding edges, those are represented here, and then to the data nodes. So in this example, we say here 4, because we are using only for this example the latitudes and the longitudes of our target nodes. But we could also use some forcing variables like the topography or any other variables, or even some input variables. You can use whatever you want. And those are passed to the decoder, which in this case updates the data nodes, right? So these are considered, if you see here, the order of the data nodes is revert from the decoding and the decoding. So in the decoder, the source nodes are these, and the target nodes are the data nodes. And we always update the target nodes. So in this case, the target nodes are the data nodes that now are updated to the physical state, 88 variables. So this is the main workflow that you have to take into account to understand the models, right? So this is really the key of a model in Anemoi. Now we will go through this. So we cover the model, right? The big picture of the model. But we talk about the encoder, the processor, and decoder. And we only said one thing, that those are also graph neural networks in the sense that they take a graph and return a graph. So what is important to note here is that both encoders and decoders are called inside of the code, they are called mappers, because they map from one grid to another, right? Remember that we both of them take a subgraph as an input, source nodes, target nodes, and the edges going from source to target, and they return these target nodes updated, right? It is the same structure for both encoder and decoder mappers, right? So they are exactly the same. And for this, we have different types of models of graph neural networks. So two of the most common things are GNN or graph transformer. For this, you need to define the graph because they rely on the graph structure. But there are other types of encoder and decoders that they don't need to rely on a graph structure, right? So you wouldn't need to define the connection between them. For example, it would be the transformer or the pointwise MLP. The pointwise is the most simple use case because it will consider the problem as a pointwise problem. So this in reality will only work when the source and target is the same. So it may sound a little bit confusing, but the idea is that it is for some cases that we have the data and the hidden course is the same, right? Because we are, for example, interested in pointwise emulation of anything, any process, right? So this allows to degenerate the graph in a pointwise process. And then similar for the processor, right? So the processor, instead of operating in a subgraph, it operates directly in one set of nodes, but we can still choose 4 different configurations that are exactly the same for mentioned before: the GNN, the graph transformer, the transformer, and the pointwise MLP. And here we see the mapping between the config file in the model. So this is the model config file, similar as we have for the graph, that we have a recipe. For the model, we also have the option to fill this configuration that you will go through it tomorrow more in depth, just to see how to use this different configuration. But the idea is that the model will have his own configuration. And here we see the 3 main components: encoder, processor, and decoder. And you can see as before that the target will specify the class used for that encoder, processor, and decoder. And then you can specify the different parameters, like the number of chunks, the number of heads, or whether you want to use, for example, I don't know, any of the other, like the sardine strategy, for example. Sardine refers to how you want to scale your model. Sardine means splitting some parts of the model across different GPUs. So you can choose these different things for different encoder, processor, and decoder, because each type of model may have a better option. So now we have covered the models and the models components, being the models component is encoder, processor, decoder. So the next component that we have here is the distribution layer. This is what I was referring, everything related to the sardine, and this relates on how to scale your model for high resolution data, where you will have to train your model not only on one GPU, but maybe in 16 GPUs, 100 GPUs, in too many GPUs, that you have to split your samples because they don't fit in memory. So there's some utility that allows you to scale these models to very large HPC. And the idea here is you will also get more details tomorrow, but you can also check the documentation if you are interested in in this content. I won't go more in depth here. I think you will have tomorrow a slide on this, and also please check the documentation. The next thing of these components is the data indices, and these data indices refer to the indices that we use internally in the model to define the input and output of the model. So we have mainly three categories of variables within Anemoi. One is a forcings variable. That means that a variable is only passed as an input. We have also a diagnostic variable. That means that a variable is only in the output state. And then we have a prognostic variable, right? That it would be the variables that are part of both the input and the output in the and the output states, right? So we have these three terms that are forcings, diagnostics, and prognostics. And the idea is that data indices will carry all of this information together within the model to know what variables are coming in and what variables are coming out. And then the last part of the model is the preprocessors, pre or post processors, because some of of these are used before doing the model prediction, and then when you do the model prediction, you have, for example, to normalize, right? So they are run before and after. And one example of this is, as mentioned, the normalizer, but there are other things like imputers. So for the normalizer, again, we will have some chunk in our big config files where we can specify the different normalizations. And this is basically, we have the options to define a default normalization method, and then on top of that, override different variables. So in this case, we said that use as a default method the mean standard deviation. So normalizing with to 0 mean and 1 standard deviation. And then on top of that, we tell the model to normalize TP only dividing by the standard deviation. And then for variables like the Lancy mask, don't apply any normalization at all, right? So you can still override some of the defaults, but this reduces the number of lines that you have to specify in your config, because you don't have to go through all the variables to specify each of the normalization methods. And then we also have another part of the config that just you will be able to specify the imputing. And the imputing, you can impute, imputing means that you will fill the nonce. So there are some variables like a snow cover or the waves that may have nonce in the data set in some part of the world. So you want first to impute those values in the input, so you don't get nonce to the model, because if you get nonce to the model, that will fail. So you want to impute those values, and then you have different methods. Similarly as for the normalizer, you will be able to impute by the mean, you would be able to impute by 0. So you have different options there. And then you also want to not compute the loss function where you have nonce, right? You are imputing those values, and the imputer, it will remove those values that are imputing from the loss function, right? So you don't compute the loss over those values that were filled previously. So with this, we cover the two most common use cases of the pre-post processor. And then the only thing that I would like to still add is the bounding. And this is an extra layer that goes after the encoder, processor, decoder. We have this bounding that just refer to an extra layer that we use normally for things like precipitation, or and it is tied to some physical variables that we want to restrict their values to a given domain. So it may be because they are positive, like total precipitation, that we may want to do that constraint already in the model architecture, or it can be others that they are a percentage, so they are constrained between 0 and 1. So we can also do that by a bounding layer. This is the case of ReLU, but it can be any other thing. And here again, we have a bounding field in the configs, and under that we will specify the different bonding that we want, in this case ReLU bonding, and then the variables that we want to do the bounding. So in this case, we only specify TP, that refers to total precipitation. So this would be the main classes and the main blocks of a model in Anemoi. And I think with this, you can ask any questions that you have in the chat. So happy to take any questions.
Yeah.
Thank you, Mario. And thanks, Anna, as well, for replying as much as you have. There's a few that we can go through. Sorry, let me just scroll through. There's a lot. So there's one. What is the functional purpose of the encoder, processor, and decoder? Is there a clear separation of responsibilities regarding spatial versus temporal learning, or is this emergent? Also, have any ablation studies been conducted to validate the necessity of this modular design?
I think that's a really good question, and it is also a really tough question. So I think always the first motivation, and it is like the encoding would only compress the information to the meaningful information. The processing would be the one evolving the state, right? So you compress the weather state to a coarse resolution, and then the processing evolves the state, and then you decode. But we see this is not happening. It seems that it is quite split what you learn. So in the decoding, there is a lot of advancing the weather state, right? Because you could still run. So if you want to roll out the model, that is something that we do a lot to forecast not only the next step, but a period of 10 days. What we do is roll out the step, right? So we run encoder, processor, decoder, encoder, processor, decoder. So if we try to skip in the second step the encoder and just process again the hidden state, we will see the performance degrades a lot. And even enforcing during training that behavior won't produce as good results and decoding back to the physical state. So it seems that this decoding back to the physical state, it has some kind of a regularization effect on the training that is quite positive for the models. And then yeah, there are like ablations study for a lot of things, but there are like too many variables and too many dimensions to explore that I think is really hard to reply to those questions.
No problem. We can try the next one. Can you explain more about the difference of transformers versus graph transformers?
Yeah, sure. Yeah, so that's a good point. Maybe something for future slides to give more detail on there. The basic difference is both of them are transformer in the sense they compute the attention between different set of tokens or different set of points. In the case of the graph transformed, it will use the edges and the connections to compute the attention between the target node and the neighbor edges defined by the edges that you define in your graph, right? So it is the graph defining the neighbors, and the transformer In contrast, it defines the neighbor by a sliding window. So we take all of the nodes in the Earth as a one-dimensional sequence, so it goes in a spiral over the Earth, and then we just apply a one-dimension sliding window to compute the cross attention. So this was the implementation on AFS because it was very fast. We were using flash attention that it is using LLMs, and this has already huge um, improvements on performance. So we will already relying on this technology just to be very fast and computationally efficient. Yeah, I think that's the main difference.
Thank you. Since GNN works with neighborhoods, is it able to describe relations from regions far apart, like it happens in teleconnections?
Sorry, can you repeat?
Since GNN works with neighborhoods, is it able to describe relations from regions far apart?
Yeah, so it would be able to define those teleconnections if you allow the model to learn those teleconnections, right? So you will have to include in your graph definition some longer edges, right? That's the example, for example, with the graph that we presented, this multi-scale trinodes. It has both very short edges but also longer edges that can go from one hemisphere to the other hemisphere. So this would support somehow of teleconnections. So there it comes the expertise of the domain scientists to know whether it should allow or not these connections in the graph, because there are some cases like downscaling where you don't want to have these longer connections across different areas in the graph. So I think that's where it is key the expertise each use case to adapt the graph to each specific task.
Okay. How does the graph design help the model represent interactions across different spatial scales?
I think relates to this point mentioned in the previous question. If you want to enforce a smaller scale, so learning very local connection, then you will define only shorter edges. If you want to allow connections from farther away, then you will define larger edges. And then it's things like the edge attributes, what information you think that it is useful, and all of that.
Okay. How can I be confident about my results? I'm new to this field. What are your advice and guidance? What advice and guidance do you have?
I think it's always useful to share results with colleagues and other people's, and then go through a validation, right? So you can train the model, and even with the training, you will have some plots, some metrics. But I think it is always important to go through inference and actually test that very close to what would be an operational setup or something like that, where you can really make sure that your results make sense.
Great. Both encoder-decoder and hierarchical architectures encode the atmosphere into a hidden latent space. So what does adding multiple hidden levels at different resolutions actually give you that a single hidden mesh cannot?
I think this is still very up to research, right? So it was motivated by some research articles that use this structure, hierarchical structure. The motivation there is that in some hidden you learn to process like large. So in the intermediate hidden you learn more small scale features, and then when you keep encoding that hidden to even a coarser mesh, you force the model to learn large scale features. So it was somehow the motivation was to split the scale of the features that you were learning into different processors, helping that. at the end, it is something that we did some ablation study, but it is not clear the improvement, because this also has like an increasing computational cost in both, in terms of memory required because your graph is bigger, but also in time to get your model training. So it is not clear what are the benefits, but you have there the options to explore these different graph configurations for your use cases.
Great. Now the very last one. When you include ocean wave ice fields in the input data, do you change the underlying hidden grid? And the fields with vertical layers, atmosphere or ocean, are treated as individual single fields, right?
So first, when you include the ocean wave and ice files in the input data, do you change the right grid? So that depends, right? That's an option. You can change it, but I wouldn't say that you will change the hidden grid based on the variables itself. You normally change the hidden based on the resolution, right? So you may want to have a similar ratio. So if our data is a quarter degree resolution, we may encode our hidden maybe like 1 degree, right? So we keep that ratio. So I would change the hidden when, instead of data using data at a quarter degree, I go to 9 kilometers data. Then I would increase the resolution of our hidden to half degree, just to keep the same ratio of encoding. But that wouldn't be based on the type of on the variable itself, but more on the resolution, or it can depend in the variable in the scales of the features of that variable, right? Because there are fields that are smoother, so it depends. It's something that you can do or you don't have to do. And the other thing was about the vertical levels. In the base, the what we saw that it was performing best was handling all variables, all pressure levels together. So all of them are treated as a node filter. So we have this, each node will have together all of the variables being set at 500 hectopascal and 750 hectopascal, two different variables. So we encode all of the variables together at each node. And we explore different things, but this seemed to be the most efficient computationally, and also in the one giving best results later in terms of skill.
Okay, great. Thank you. I think that's all we have time for. Thank you so much, everyone, for attending today's webinar.